reference statement see S equal to 0. In S equal to 0, we need to reference statement original positive order. Right? We out of the this actually is to be अच्छा सिर्फ जीवन प्लेइंग में हाँ but service is going to be on the day but the form position after you might go on and follow it we do have to be get working say and already the already the training is only और मतलब इसमें डॉट ठीक है तो ये यूजर वाले
Hello everyone, we shall wait till 6:05. After that, we will start the session.
इसमें ऐसा कोई बात नहीं आया delta I one even one score happens but I think also delta is delta is interesting then we can try some matrix that will be 2 or 3 seconds say exact problem even should give it demand what we want to we get there in that we can do what we I'm not we do one zero zero one we accept that by definition all numbers Here, again, yes, it's a point towards the multiplier, yes, yes, A basis. And I was that's a J कहाँ से नॉलेज ब्रेक करना पड़ेगा ए इन जी डेल्टा ई ए के वन डेल्टा ई डिफाइन
So hello all, it is 6:05 now, so we will start the session. So welcome to the week 6 of live session of solid mechanics. I am Manoj Shikhar. I am a PMRF scholar at IIT Delhi. I am pursuing my PhD in the Department of Applied Mechanics at IIT Delhi. I've done my BTech and MTech from IIT KGP. And I will be taking your sessions on every Tuesday from 6 to 8 p.m. In these sessions, I will try to discuss the concepts we have already studied in the last week, in week 6, as well as I try to solve some numerical problems. Before the start of the session, I'd like to say one thing that please do not ask any questions which are part of currently active assignment. We are not allowed to help you with those. We will solve problems on the similar level so that you will be able to understand the concepts and grasp the concepts properly. So let's move on to the content of week 6. So first of all, happy Teachers' Day to all of you. Now, in our class, we'll first recapitulate whatever we have studied in last week. And the lectures were stress-strain relation, linear relation of anisotropic materials, stress-strain relation for isotropic materials. Now the notes of these lectures which have been covered in NPTEL, you can find those from the following website. This is the website of Professor Ajit Kumar. And and you can download the PDFs from there. These PDFs, they have small questions as well as subjective questions. First of all, am I audible to all of you? Sorry, I forgot to ask that. So you can go to this website and download the PDFs. At the end of the PDFs, you will have many questions. Some of them are objective, some of them are subjective, and those questions will prepare you for different competitive examinations. In this class also, I'd like to take some of those questions. I will not solve all of them. I will solve few of them, and rest you can solve by yourself, and you can ask me doubts in the next class. So let's begin the session. You just give me 2 minutes. So first, let's discuss a few important formulas, and after that, we can move on to solving the problems. So I hope you remember the equilibrium equations we have derived already. So let me write those here because we will be using them in the questions today. So this is the linear momentum balance. P sigma. I shared my screen now. Now the question is, why do we need to know stress-strain relationship? If you look, like this is the linear momentum balance, LMB, and from AMB we know that off-diagonal elements are equal. So this is what we get from AMB. So total number of unknown sigma will be 6. If we do not invoke A and B, the total number of unknowns will be 9. So in our case, we are considering the Cauchy stress tensor. So we have 6 unknowns in the sigma matrix. Now, if you look at the LMB, we have only 3 equations and we have 6 unknowns from sigma matrix, and we have 3 unknowns from this acceleration. This body force will be known. This will be given whatever kind of body force is acting, for example, electrostatic body force or gravitational body force. You will be knowing this part. These are known. And you will write accelerations in terms of displacement. Should change the color. You can write these in terms of displacement. So we have we have 6 unknown from sigma matrix, and we have 3 unknowns. Displacements are unknown too. So these are unknowns. So we have total 9 unknowns, and we have only 3 equations. The number of equations we have are 3. So we need extra equations to solve for sigma ij and displacements ui. Thus, we need stress-strain relation. These are also called constitutive relations. I will skip the derivation part. I will just give you the important formulas so that we can move on to the questions as quickly as possible. So all the components of sigma. First of all, one declaration. In this course, we are assuming that the relationship between sigma and epsilon will be linear. Okay, so for your course, the relationship between the components of stress tensor and components of strain tensor will be linear, but in general, it could be any function. So for example, just for the sake of introduction, we can write sigma is equal to function of epsilon 1, epsilon 2, epsilon 3. So in general, this function can be all sorts of this can be all sorts of function. But for this course, we will mainly focus on the linear relationship. We shall mainly focus on linear relationship between sigma ij epsilon I. Okay. Maybe I should write epsilon mn because these are different indices. Okay. So in class, sir has already shown you that how to find the elasticity tensor. So I will directly write the formula and I will write the about symmetry also. So Cijkl is a stiffness tensor, fourth order stiffness tensor. And this is given by del sigma ij by del epsilon kl. When epsilon kl tends to 0 or equal to 0. And the final expression which we get is sigma ij equal to Cij kl epsilon kl. And you can see that kl, k and l are repetitive index, also known as dummy index. So there will be summation over k as well as l. Now, if we just look atCijkl, and I can vary from 1 to 3, j can vary from 1 to 3, and k and l similarly can vary from 1 to 3. So total number of independent components at first glance will be how many? 3 to the power 4, 81. But if we look carefully, we will understand, we will be able to see that actually there are lesser number of independent components than 81. For example, there are two different kind of symmetries we will talk about. The first one is minor symmetry. In minor symmetry, what happens? We know that sigma ij is equal to sigma ji. Okay, so if I replace sigma ij by sigma ji, the same thing will happen here also. So let me write it for you. That has already derived it in the class, so I will not go in very deep. This is equal to sigma ji. So if I want to write sigma ji, then what will be the right hand side? It will be Cji kl epsilon kl. So from here, what do we get? We get Cij kl equal to Cji kl. Another kind of symmetry, another part of minor symmetry is that epsilon ij is equal to epsilon ji. Because strain tensor is symmetric. If you remember, the formula for strain tensor was 1 by 2 gradient of u plus gradient of u transpose. So we know that A plus A transpose by 2 is a symmetric tensor. or symmetric matrix. Since this is a case of two second order tensor, so it's a symmetric matrix. So if you do epsilon I is equal to epsilon ji, so from here, what we can do, so from here we get Cijkl equal toCijlk. And from major symmetry, I will directly write this one. Its proof is really long and sir has already done this in class. From major symmetry, what do we have? We have Cijkl equal to Cklij. So after incorporating all the major and minor symmetries, we can conclude that C tensor will have 21 independent constants. Okay. So any general material, if you make a stiffness tensor for any general material, the maximum number of independent constants you can have is 21. And these materials are called anisotropic materials. You may have also read triclinic, the word triclinic somewhere. So anisotropic materials are also triclinic materials. So anisotropic material or triclinic material will have 21 independent constants in their stiffness tensor. So this is generally asked in the GATE exam also, depending upon the material type. For example, orthotropic material will have 9 independent constants. I will mention it here. Orthotropic material, 9 independent constants. Then transversely isotropic. Material will have 5 independent constants. And isotropic materials will have 2 independent constants. Then there was a concept of Voigt notation. So in Voigt notation, we replace the sigma matrix by a sigma vector, so by stress vector, and the components are filled like this. So just to remember, you can remember this direction in the matrix, sigma matrix. There are actually various kinds of Voigt notation being followed, and to avoid confusion, just remember this direction, which we will follow in this course. So we will first move towards diagonal from sigma 11 to sigma 13. Then we will move upwards till we reach sigma 13, and then we will move towards sigma 12. So if you look at the sigma matrix, you can see that I have written the same in the similar order. First, I've written sigma 11, sigma 22, sigma 33, then sigma 23, sigma 13, and sigma 12. Sometimes these components, they are also replaced by a single number. For example, you may find that some books replace 1 by 1, 2 by 2, 3 by 3, then 2 by 4, 1 by 5, and 1 by 6. So this will also depend upon the literature you are following. I have seen different notation also while going through different research papers. But the one I'm showing you here is the most widely used. Similarly, now we have to be careful while writing the strain tensor in void notation. So in a strain tensor, it is written as epsilon 11, epsilon 22, epsilon 33. Till now there is no issue. But now while writing the shear part, we are actually writing the total shear strain. So if you remember the matrix form of strain tensor, the off diagonal element, they were gamma by 2. But here, when you write in the void notation, it is actually gamma. So if I'm writing the gamma 23, in the matrix representation of epsilon, it will be gamma 23 by 2. But in the void notation, we are directly writing the gamma 23. So just keep this in mind. I've seen students making mistakes and losing marks at this place because after while if we ask them to calculate some stresses and we give them a stiffness tensor and we have given them the strain matrix, they directly write epsilon 23 instead of gamma 23 here. And thus the calculation becomes wrong. So keep this in mind. So this is the constitutive relation. This is a 6 cross 6 CIJK matrix. This will be your strain matrix in void notation. Now we will talk about a specific material called isotropic material. Now there are two words here I'd like to discuss. First, the word isotropic. Isotropic means suppose here we have a point, and if we want to know, let us assume we want to measure a property Young's modulus at this point. Now, if I move in this direction, suppose if I am getting some Young's modulus even, if I move in this direction, I'm getting some Young's modulus E2. I'm moving in this direction, I'm getting some Young's modulus E3. And similarly, if I move in different directions, I'm getting some value of Young's modulus. Now, if it at this point P, any direction in which I move, suppose we are getting the same value of stiffness irrespective of any direction in which I am moving. So in that case, this property is same in all the direction at that point. So this property is called isotropic. That the property is not changing with direction. In any direction, you will get the same value of the property. Now the other word is homogeneous. Homogeneous means suppose we have a body and we are taking two different points or any points we can take. Suppose currently we are looking at these 2 points. For example, now if I'm measuring some property here, let us assume again we are considering the case of Young's modulus. If I'm measuring Young's modulus here, and suppose if I'm going in this direction here, I'm getting E1. In this direction, I'm getting E2, and so on. Here also I do the same thing. I go in different directions. And I get different Young's modulus values. Now, suppose if I move, suppose this point is P and this is Q. If in P, if at point P I moved in a particular direction and I got some value of Young's modulus. And at point Q, I moved in the same direction. And if I get the same value, like if I get E1 only, suppose E1 star is equal to E1, E2 star is equal to E2, and so on. Then these 2 points are homogeneous, like we are getting the same value of the property in a direction at 2 different points. Now suppose if it is happening at all the points of the body, then we tell that body is homogeneous. So the contrast is in isotropic material at a particular point, the property will be equal in all the directions. Okay. In case of homogeneous, at the same point in different direction, the value of properties can be different. But if I take another point and if I move in the same direction, I should get the same value of the property. So there is another metric. So in general, for UG courses generally, UG solid mechanics course, we consider isotropic homogeneous material. If here what happens? Here, you take any point on the body, you move in any direction on the at that point, you will get the same value of the property. So this body will have same E at any point. And any direction at that point. Okay. So one thing I'd like to mention here, I took the example of Young's modulus. So this body is isotropic and homogeneous with respect to Young's modulus. Like the Young's modulus of this body is same at every point and is independent of any direction we take at that point. Similarly, in solid mechanics, we have modulus of rigidity G. That will also be same at every point because we have considered a material like that. But it may happen that this material is not isotropic and homogeneous for some other property. Suppose if I take the example of electrical conductivity, or if I take the example of, let us assume the temperature distribution, how will the temperature distribution happen on the body? So isotropic and homogeneous is with respect to what kind of property I'm talking about. So in solid mechanics, mainly we talk about Young's modulus, modulus of rigidity, or Poisson's ratio. So for those, isotropic and homogeneous. Now I will give you some formulas which we will be using today. So sigma is lambda, one of the Lame's constants, trace of epsilon matrix, delta is a, this is the Kronecker delta function, okay, plus 2 mu epsilon is. So this is one of the formulas. Now for isotropic material, the formulas are this. C11 is lambda plus 2 mu. C12 is lambda. C22 is equal to C11. C33 equal to C11 because we are considering isotropic material. And this will be equal to C13 and C23. And C44 equal to C55 equal to C66 equal to mu. Now what are these CIJs? So I will write it here. So the stiffness matrix, 6 cross 6 stiffness matrix SOD can be written as this will go to C61. Okay. And here it will go till C66. This will follow the same trend, whatever it is happening. Anyways, so this is a generic C matrix. Here also you will have some, let me write only. So this is a 6 cross 6 matrix. Okay. Now for isotropic material, we can plug these values and all otherCijs will be 0. All otherCijs are 0. Okay. So for isotropic material, our matrix will look like this. C11, C11, C11. This is C12, C12, C12. So this is how the stiffness tensor stiffness matrix will look for So here we can directly, so sometimes you can directly use this matrix and you can use these things also. Now there are different relationships you may have read between E, G. So G equal to what? E by 2 into 1 plus mu. Okay. And G is also equal to mu. So keep this in mind. Now what is mu? Mu is Poisson's ratio and it is defined as lateral strain by longitudinal strain. So this is a ratio of negative sign. Negative sign it should. And there is other property called bulk's modulus, and we can write the bulk's modulus by E by 3 into 1 minus 2 mu. And by definition, this is so let's move on to the questions for today. So first we will discuss the questions which are at the end of the lecture notes available on Professor Ajit's website. So question number 5 from lecture 16 will be, think of a uniaxial tension of a solid circular cylinder. What can you say about the Mohr circle of this? It's a state of stress. So they have given uniaxial tension of a solid circular cylinder. So how will our stress matrix look? Anyone can talk. If any of you have any doubt till now, you can ask me. Otherwise, I will go on to solving the problems. So lecture 16. First time I will be going through objective questions. So question number 5. Okay. So they have given you that cylinder is uniaxially loaded in tension. So our stress matrix will look something like this. So from here, what can you say about the principal stresses? So there are 3 principal stresses. Lambda 1 is sigma 11. Lambda 2 is equal to lambda 3 and it is equal to 0. How was I able to tell that sigma 11 is the one of the principal stresses? Because off diagonal terms are 0 here. So this state of stress is principal stress, state of stress. Okay. And the diagonal elements, they will be the eigenvalues or the principal stresses for this state of stress at a point. I hope I have made myself clear. Now to draw Mohr circle, what do we do? Suppose if this was sigma xx, sigma xy, sigma xz, and so on. So what do? We plot sigma yy. So in this case, sigma yy is 0. So this is our, maybe I should change the color here so that we'll be able to visualize. So this is sigma yy. Then we plot sigma xx. So sigma xx and sigma yy. How do we find the center? Center of Mohr circle? This is sigma xx plus sigma yy by 2. So this will be sigma 11 plus 0 by 2. So sigma 11 by 2. So here we have 0. Here we have sigma 11. How then what we do? We have plotted the center. Here we have center sigma 11 by 2. We plot the sigma xy component. What is the sigma xy component? It is 0. So this becomes our radius. This is our radius. This is our radius. Now we have a center, we have a radius, we will draw the circle. I hope you were able to follow me. This is sigma and this is tau axis. Okay. So this is our Mohr circle. Now let's look at the options. What are the options? Mohr circle will pass through the origin. Mohr circle is passing through the origin. So option A is correct. Mohr circle center will be at origin. This is false because Mohr circle center is where? It is at sigma 11 by 2 comma 0. Radius of Mohr circle will be equal to the applied tensile stress. This is false because we have already seen the radius is what? Radius is what? Sigma 11 minus sigma 11 by 2. So radius is sigma 11 by 2, half of the applied stress. So only option A was correct. Only option A was correct. Now, question number 6. A material X is formed by engraving two families of fiber perpendicular to each other in an isotropic material. So what they have given? They have given you that there is some isotropic material. Suppose this is the isotropic material I have drawn. Okay. Now in this, what we are doing? We are using two different kinds of fiber. I think we are embedding. Just let me look at the word. We are engraving two different kinds of fiber. Okay. And how are we engraving those fibers? They are perpendicular to each other. So red part was our, so this whole part. Okay, red was a solid part. I did not show the solid. So it was an isotropic material. Then what we did, we inserted two different families of fiber, the yellow family and the blue and the, what should I say, algae green family, and they are perpendicular to each other. So now the new material we have got is, they have named it as X. Now they're asking, X is an example of. So if you had followed the last week's lecture, you would have known that X is orthotropic. Why is it orthotropic? Because in this direction, if we move, sorry, I should use the yellow color. So for the timing, if we move in this direction along the fiber of the blue line, we will have some property E1. In this direction, we will have something E2. And if we move in the third direction, in the direction of isotropic material we already had, we will have something E3. So we in three perpendicular directions, we have three different properties. So the material X is orthotropic material. And what is the follow-up question? The follow-up question is the number of independent material constants for material X is. So now we know that X is a orthotropic material. So number of independent constants, how many it should be? It should be 9. Is 9. So this is the solution for question number 6. Now question number 7 is, we have two different, we have to say that if it is true or false. We have two different linear stress and strain relations for isotropic materials. One of them should be used when two independent material constants are present, and the other one should be used when three independent material constants are present. So this statement is false because for isotropic materials, we have only one linear stress strain relationships, and also we have only two independent material constants. We don't have three independent material constants. So this statement is false. Now question number 8 is a body is in a plane stress condition in XY plane with Z being the normal to the plane. Which of the statement is correct? So if you remember, the plane stress means any stress out of the plane will be zero. So this is a very good question to clear your concepts. So I will just deal with this in slightly more detail. So suppose we have a very thin plate. OK, so we can assume that we have a plane stress condition. So in this case, they have given the plane as XY. And they have given the third direction as Z, which is out of plane. So sigma XX will be non-zero. Sigma YY will be non-zero. And sigma YX or sigma XY will be non-zero. Now which stresses will be zero? Sigma ZZ, sigma XZ. Any stress which has a Z will be zero. Now here is the interesting part where the students make mistakes a lot. What they will do, they will think, OK, plane stress condition. They will also consider the strain to be planar. But for plane stress condition, there could be out of plane strains there. So out of plane strains will not necessarily be zero. So you have to keep this in mind. Oh, not zero. So strain tensor can have all 6 components present in case of plane stress condition. If it was a plane strain condition, then out of plane components of strain would have been zero. But in that case, all 6 components of stresses may have been present. So keep this in mind. Do not make this mistake. So according to this, which option is true? Sigma XX, sigma XY, and sigma YY is not equal to 0, and epsilon ZZ is not equal to 0. So this option is correct. Now, in this question, there's something I'd like to mention. Linear elasticity implies a linear relationship between stress and strain. This is what they have given, and they're telling which of the following is true. Now, the first statement is normal components of stress tensor are linearly related to normal component of strain tensor. Normal components of stress tensor are linearly related to shear components of strain tensor. OK. The third part is shear component of stress tensor are linearly related to normal components of strain tensor. And the fourth is all normal shear components of stress tensor are linearly related to normal / shear components of strain tensor. So the correct answer is D if it is a single choice answer. Suppose if you have to pick only one of the answers, then the correct answer is D, because all normal shear components as well as of stress tensor will be linearly related to all normal / shear component of strain tensor. But if it is a multiple choice, multiple correct question, then these statements are also true because these are a special case of the fourth. Here, normal components of stress tensor are linearly related to normal component of strain tensor. This is true. They are also linearly related to other shear components, but they are linearly related to normal component of strain tensor also. So for multiple choice, multiple correct option, I think all 4 should be marked. For a single choice question, only D should be marked. OK, we will come to question number 10 later on because this is a big question. I will first discuss the smaller objective questions, then I will move on to the longer ones. It will take almost 15, at least 15 minutes. Question number 10 will take at least 15 minutes. So question number 11, they have given us that our 200 mm, 100 mm, 200 mm cross 100 mm cross 50 mm cross steel block is subjected to a hydrostatic pressure of 15 MPa. The Young's modulus and the Poisson's ratio of the material are 200 GPa and 0.3. Then the change in volume of the block will be. So they have given you what? They've given you that you have a block. This is 100 mm. This is 200 mm. And this is 50 mm. So the volume of the block is 200 into 100 into 50 cube. Okay. So they've given you the volume. They've also given you that a pressure of 15 MPa. So what is the property of pressure? It acts normally only. And it is a compressive load. Okay, pressure is a compressive load. So we will write it with negative sign. They have given you the pressure. Now they have also given you that E is, I think 200 GPa. Okay. Yeah, 200 GPa and mu is 0.3. Mu is 0.3. They're telling you to find what is delta V. So how will you find delta V? We will use the formula for Young's modulus. Bulk modulus. This is what? Minus P delta V by V. And we can equate it by the formula E by 3 into 1 minus 2 mu. So I will convert everything in the SI unit. Now we will put the values of pressure which we have. So it is pressure is minus 15 MPa. Now this delta V will be here into this volume will go above. So here we will have so we have 5 by 3 equal to 15 by delta V. So we have delta V as 90 into 10 power minus 9 meter cube. So this is 90 millimeter cube. Let's see if we have that option. So option B is the correct answer. Question number 12, what will be the volumetric strain at a point in an anisotropic body if it has pure shear state of stress at that point? Okay. So what is the formula for volumetric strain? It is delta V by V. Okay. They have given isotropic. So we know that we have some value of K, some finite value of K. So what we can do, we can write K as minus delta P divided by delta V by V. Now, if you look at the question, they have given you that pure shear. Okay. Pure shear. So sigma is what? It will have only off diagonal elements. And since they have given so we have only off diagonal elements in our stress matrix. Now, what is the value of delta P? If you remember from the class, it will be 1 by 3 into trace of sigma. So what is trace of sigma? 0. So here delta P is 0. Okay, so what we can do, we can write delta V by V as minus delta P by K. And thus delta V by V will be 0, implies that volumetric strain is 0. And actually, this should come anyways. For example, if you remember when we were reading the stress tensor, there we had split the stress tensor into two parts. One was the deviatoric part, and the other one was the part in which only normal components of stress were there. Okay, so the first part where the normal components of stress were present, what was its function? It was changing the volume of the body. The deviatoric part was changing the shape of the body. So pure shear is what? Pure shear is, you can look at it, it is like the deviatoric part of the stress tensor. So it will not change the volume. Hence, the volumetric strain will be 0. I could have said that directly, and I could have directly said that this one is 0, but I wanted to show you how to calculate it. Now, question number 13. The theoretical limit of Poisson's ratio in an isotropic material is -1. Of which of the following information is used to obtain this limit? So in the lecture, sir has discussed this, the shear modulus of elasticity and Young's modulus of elasticity. They are positive quantities, and these two actually put the limit on -1. Now, also this statement is wrong that Poisson's ratio is -1 corresponding to incompressible material. It is actually 0.5. Just 0.5 for incompressible material, and this comes from bulk modulus formula. There we have E by 3 into 1 minus 2 mu. So 1 minus 2 mu cannot be negative, and that's why we get the limit, that maximum limit, that mu can be 0.5 only. So for incompressible material, mu is 0.5. Now question number 14 is, suppose the stress matrix at every point on the body is same. Okay. Furthermore, all the columns of the matrix are same. Which of the following holds true? So let's say our stress matrix is what? They're telling that all the columns are same. So suppose if I take sigma 1, 2, sigma 1, 3, then this will also be sigma 1, 1, sigma 1, 2, sigma 1, 3. This will also be sigma 1, 1, sigma 1, 2, sigma 1, 3. Okay, so this is our stress matrix. Now, what do we know from AMB? From AMB, we know that off diagonal elements are equal. Not say that off diagonal elements are equal. Sorry for that. I should say sigma ij is equal to sigma ji. This says that our stress matrix is symmetric. So this forces us to write sigma 1, 1 equal to sigma 1, 2 from here. Then sigma 1, 1 equal to sigma 1, 3. So what happens to our stress matrix? It becomes sigma 1, 1 everywhere. So the questions are, does it correspond to uniaxial tension of the body? We can see that for uniaxial tension, what will happen? All the components of diagonal elements, all the components except the first will be 0. But here they are not 0, so it is not uniaxial loading. For case of biaxial tension, we will have first and second, and sigma 1, basically the first row, first column, second row, second column, and all other will be 0. And for triaxial loading, we have first, second, and third, and all other are 0. So the answer is D. None of these. Consider an isotropic material which does not go any deformation in transverse direction. When it is stressed, the Poisson's ratio for such material will be. So I can directly say the answer is 0, but still I will show you. So what is the formula of Poisson's ratio? It is minus lateral strain by longitudinal strain. So what they're telling is the longitudinal strain is 0 because we suppose if we are stretching it in XX direction, there's no deformation in YY direction or ZZ direction. So epsilon YY and epsilon ZZ is 0. In that case, mu is what? 0 by some, let us say epsilon XX. So this is 0. Hence, option C is correct. The slope of a normal stress versus the corresponding normal strain curve in the case of uniaxial loading is elastic modulus. Elastic limit is the point up to which, if the load is removed, original volume and shapes are regained. True. Because after elastic limit, you won't be able to regain the volume or shape of the body. Which of the following is a dimensionless quantity? So shear stress has a dimension of Pascal. Poisson's ratio is the ratio of two strains. It is dimensionless strain is dimensionless. Poisson's ratio is negative of lateral strain by longitudinal strain. True. A dimensionless quantity. True. The change in the length of a vertical bar due to its own weight as compared to the that of when the bar is placed horizontally and subjected to a direct axial load will be equal to its weight. Okay, so this is a very good question. Like I can directly give you the formula also, but I don't know if you will be able to feel the. I will also solve it. So question number 20. Okay. You have two scenarios. In first scenario, you have a rod. It is hanging from a wall. And let's say the total weight of the rod is W. The length of the rod is L. Okay. And they're telling you that what will be the delta. So delta is given by W by two A. Okay. Where A is what? A is the area of cross section. In scenario 2, they have given that they're telling that you're applying the same force W here. This is on a horizontal table. So this is on a horizontal table. And you're applying a weight W. So the effect of gravity is not there. You're applying a weight W. Sorry, a force which is equal to W. Here, so I will write it delta weight. I will write delta force, maybe delta W directly. So here the total elongation is W by A. And according to question, they are asking what is delta W, weight by delta W. So what is it? W by 2A divided by W by A. So answer is 1 by 2. So answer is C. Now I will show you that how you can prove this also. Okay. Actually, it will be WL here. Sorry. Which the dimension was not matching. This should be in something meter or millimeter, and W and A were getting cancelled. So it should be WL by 2A. Now I will derive that how delta weight is WL by 2A. Okay. It might just save this one because this is hanging. So we know that A is the area of the cross section of this rod. L is the length of the rod. So what is the weight density? This will be total weight of the rod divided by the volume. So what is volume? A into L. So I will denote it by rho. Now, let's suppose we are considering a section dx here. Okay. Length of the bottom part is x. So this will be what? L minus x. So what will be the force acting on this dx part? It will be the weight of the part which is hanging below it. So what is the weight of the part hanging below? I will write it. Let's say I will name it A, B, C. So weight of BC, what is weight of BC? This is rho times rho, the density times area of the cross section into L. Now, in this case, the assumption is that area is constant. That's why I'm able to write A here. Suppose if area was not constant, we would have find the total volume here and we would have written rho as W by total volume of the rod. And here it was AX then. Weight of BC will be AX. Okay. So this is the, sorry, here it should be X, not L. Why did I write L? Here it will be X. So if we replace rho by WAL, what we have W into X by L. This is our weight of the hanging part, the BC part. OK, and that weight will cause the elongation in this delta X. So what will be delta? The total elongation. It will be 0 to L, 0. Our X is like this. OK, 0 to L. So what we are doing, we are basically summing the deflection of all the small dxx. Suppose we had some portion here or here, whatever deflection they had, we are summing that. So the sum, so in maths, we know that we can replace that by integration if the dx are very small. So the same thing is written here. Now for a small dx, what will be the delta? It will be force on that. Maybe I will write it as Wx. So Wx by AE into dx. So this is the Wx is what? The weight of this hanging part, and that hanging part is pulling this dx portion, right? That hanging part is pulling this dx portion. So Wx by AE into small dx will be the total deflection of the small dx part. So now we replace Wx by W into X by L, and we integrate from 0 to L. So for our case, we know that W and A and E and L are constant, so we will take them out. So thus we have an integration of X from 0 to L. So this will be what? W by AEL into X square by 2, 0 to L. So W by AEL into L square by 2. So the total deflection, this is like delta weight, is what? WL by 2AE. I hope you have understood how to calculate the deflection due to self weight. What were the assumptions? The area of cross section was constant. The length was capital L. And if the area of cross section is not constant, you will have to replace AL, whatever I have found rho here. Here AL will be replaced by the total volume of the rod. Here A will be a function of X and so on. You can look at some other standard books for different kinds of problems. Okay. Anyways, so let's move on. Question number 21 is a thin circular plate of uniform thickness is subjected to pressure as shown in figure below. So in this case, you can see that y axis, the z axis is the out of plane axis. So this plate is getting pressurized. So this is the case of plane stress loading. So any component with z in this stress will be 0. So normal stress is 0 in z direction is correct answer. What is the range in which Poisson's ratio can take its value for linearly isotropic body? So we know that for linearly isotropic body, Poisson's ratio lies from -1 to 0.5. The limit of -1 comes because the modulus of elasticity and the modulus of rigidity, they have to be positive. So from there we get the limit -1, and the limit 0.5 comes from the bulk modulus. It should be greater than 0, and that's why if you go by its formula from denominator, you will get that mu should be less than 0.5, less than equal to 0.5. Okay. Now question number 23 is the body undergoes a deformation as follows. So they have given you the deformation map, ux equal to ay, uy equal to 0 and uz equal to 0. This is also called a simple. Okay, so this is the example of simple shearing of a body. You can see that you are applying a load, you are applying a displacement in x, which is dependent on y. Here A is a constant, so they have given you that A is a constant, denoting the amount of shear. Assuming the body were isotropic, which component of stress would be non-zero? Okay. So it's quite pretty straightforward. I will just write it here. So what was the formula for stress? Okay. Now they have given you that ux equal to ay, uy equal to 0, and uz equal to 0. So what is epsilon xx? It is 0. Why? Maybe I'll write the formula. Del ux by del x. It is 0. Epsilon yy equal to 0 because it is nothing. No function of y is there for u1. And epsilon zz is 0. Okay. How will we find the epsilon xy? Or gamma xy, I should say. Gamma xy is del u so this is what? A plus 0. Gamma yz is del u y by del z. Gamma xz is okay. So for this displacement, we have only gamma xy is not 0, right? Now we will plug this here in sigma ij. So for sigma xx, first of all, let's calculate trace of epsilon because that will be used. So we know that trace of epsilon is what? Epsilon xx plus epsilon yy plus epsilon zz, and they are all 0. So this is equal to 0. So sigma is what? 2 mu epsilonize it. Okay. Because stress E is 0, stress of epsilon is 0. So our formula reduces to 2 mu epsilon Iz. Or we can write it as mu into gamma Ij. So if I and j are equal, gamma 1 1, there is nothing called gamma 1 1, so it will be 0. Okay. Maybe I should write epsilon Iz here because give me 1 minute. I think. Let's keep it as epsilon Iz only. Okay. So into epsilon Iz into mu. So if I and j are 1 1, 2 mu epsilon 1 1 0. The same is true for now if I is x and j is y, then sigma xy will be what? 2 mu epsilon xy. So this is basically 2 into gamma xy. So this is a times mu. Sigma yz is what? 0 because epsilon yz is 0. Sigma zx is 0 because because gamma xz is 0. So the only non-zero component is, though these questions are pretty small, I'm showing you the steps so that in exam you do not get confused if you're not remembering the basic concepts. You can directly use these formulas. So the answer is tau xy or sigma xy. Just give me a few minutes that I can drink water, and so we will take a short break of 5 minutes, and after that we will again restart the session. So welcome back. Uh, let's move on to question number 10, which I had skipped at that time because it was a long question. And this question will touch different concepts you have studied till now. So question number 10 is, think of a rubber cube which is inserted within a cavity in steel block. Okay. Keep hanging. So what they have given? They have given you. They have given you a question where there is a cavity here, and this cavity they have filled with a rubber cubes, and the size of the cavity is same as the size of this rubber cube. Okay, the cavity is actually in one of the steel blocks, and they have told you that the top surface of the rubber, like this is the top surface of the rubber, it is getting pressed by another steel block, and the pressure with which they are pressing it, it is uniform, and they have given it the value P pascals. Okay, they're telling you that assume the steel to be rigid and that there is no friction between steel and rubber. So this is basically why no friction between steel and rubber, so that you don't get any traction components in the in this direction or in like other direction. Okay, and they're asking you which of the following is a true related to longitudinal strength. So question number 10. So you have a cavity here. Please do not judge my drawing. And they have filled it with some rubber. Okay, they have filled it with some rubber. And what they're telling is that they are basically they are applying some force. Basically, they are applying some force P here. You can think it like that. And they are applying P here. Some pressure P here. And to apply that pressure, they have used SB. Let's draw what they have given in the. So there is one steel thing here, and they're applying pressure P on this steel. And since the steel is rigid, it will not deform, and the whole pressure will be transferred to the rubber. Now the question is, what will be epsilon xx, epsilon yy, and epsilon zz? So first of all, look at one of the information, rigid. Steel is rigid. This means what? If I'm applying pressure from here, okay, the steel cannot deform in other x and y direction. So this is suppose y, this is z, and this is x. We are applying load in the z direction. So sigma zz is minus p. Okay, we are applying load in the z direction. The rubber cannot deform in x or y. Why? Because it is getting stopped by the steel surrounding around it. That's why ux and oh, it is hanging again. Every time at the end of the class, it starts hanging. So ux is 0, uy is 0. Only thing which is non-zero is uz. So uz can be taken as a function of x, y, and z. Okay. Now, till now we have not assumed that uniform pressure is applied. Okay. Now they have also given that they are applying uniform pressure. Okay. The applied pressure is uniform. The applied pressure is uniform. So what does this mean? This means that any cross section you take here, any cross section you take, all these blue lines, they are actually planes. These kind of planes. Any cross section you take, you will have same UZ with UZ variation in X and Y. Okay. So in X and Y, you will have same UZ variation. This means that UZ is independent of X and Y, and UZ simply becomes a function of Z. Okay. So, sorry. So this was what? These were vertical cross sections. You cut the rubber using vertical cross sections. I drew it wrong here, so I will again redraw it. So what we are doing, suppose let's draw slide, let's draw from different angle. Okay. Maybe I should change the color. Let us assume this is our rubber block. This is our rubber block. Okay. So this direction is Z. Now we are cutting it like this. So on these planes, we will have same UZ. Hence, UZ becomes the function of Z only. Now we know the deformation map. We know UX, UY, and UZ. So what will be epsilon XX? It will be del UX by del X. So it will be 0. Epsilon YY is del UY by del Y. So it is 0. And epsilon ZZ is what? Del UZ by del Z. So this is not 0. Okay. So the answer to this question is will be 3. Now they're telling you that find the norm. What basically they're telling normal stress in X and Y direction in this problem. So you have to find what is sigma XX and sigma YY. Okay. So for this, let us first find other components of strain tensor. So what will be gamma XY? So this is 0 because UX and UI are 0. Gamma XZ will be 0 because UZ is only a function of Z, and gamma YZ will be 0. So our epsilon tensor is basically so from relation of stress and strain, what we can infer? We can say that gamma, sorry. So we know that tau ij is gamma ij by G. We are taking G here because they have given isotropic material. Okay. Now we know that all the gamma ij's are 0. So tau ij is 0. So basically tau xy equal to tau yz equal to tau zx equal to 0. Why? Because all the shear strains are 0. So if you keep on plugging them here, you will find that, okay, for xy, I equal to x and j equal to y, here I will plug xy and it will come to 0. For yz, I will put this strain and this is 0, so this is 0. Xz, this is strain and this will be 0. Okay. Now I've written xz here and zx here, so it doesn't make a difference because our stress and strain tensors are symmetric. Keep that in mind. Now we know that epsilon xx, what is it? This is 1 by E sigma xx minus nu times sigma yy plus sigma zz. Okay. Similarly, epsilon yy will be what? 1 by E sigma yy minus mu times sigma xx plus sigma zz. Now, if you look at the problem, you can understand that this problem is symmetric because we are applying the force from z direction, but the other two directions, they are symmetric, and they have given that it is a cube. They have given a cube here. So if you remember, they have given a rubber cube here. So from the symmetry of the problem, we can see that sigma xx and sigma xx and sigma yy are equal. But why are they equal? Because the same reaction is generated from steel walls in the both direction. Because same reaction are generated by steel. In both directions. Okay. That's why sigma xx and sigma yy, we can see from the problem that they are 0. Now there's one more thing to see here, that you can see that epsilon xx is 0 here. Okay. That does not mean that our sigma xx will be 0. So I will use this here. So we can replace this by sigma xx minus mu times sigma xx plus sigma zz. Okay. So we have got 0 equal to 1 by E sigma xx into 1 minus mu plus, minus mu times sigma zz. Okay. So from here, we actually get the relation between sigma xx and sigma zz. So what is the relation? Sigma xx is equal to mu times sigma zz divided by 1 minus mu. Okay. And now we know that what is the external pressure? External pressure they have given as P. So our answer will be minus of, we can replace sigma zz by minus P. So they had given sigma zz as minus P. Where is it? I've written it somewhere. So sigma zz is minus P. So our answer is sigma xx equal to minus P times nu by 1 minus nu, and sigma xx and sigma yy are equal. So the answer will be the third option. Okay. Now they're asking the volumetric strain will be equal to. Now, what will be the volumetric strain? So volumetric strain is what? Trace of epsilon. So this is epsilon xx plus epsilon yy plus epsilon zz. So these two are 0. So basically they are telling us to find del uz by del z. Okay. Now how do we find del uz by del z? So we will use the equilibrium equation. The equilibrium equation in the z direction is what? Del sigma zz by del z plus del sigma xy or tau xy by, oh, sorry, it's not xy, xz. By del x plus del yz by del y plus bz. This is equal to rho times az. Okay. We know that sigma xz is 0. So this becomes 0. We know that sigma yz is 0. This becomes 0. There is no body force given. So this is 0. And rho az. So az is 0 because they have not given any acceleration. So what are we left with? We are left with sigma del sigma zz by del z is 0. What does this mean? This means that sigma zz is constant with respect to z. This is constant with respect to z. This is what we get. Okay, so this means that sigma zz equal to minus p throughout this. So throughout the rubber block, sigma zz will be minus p in the z direction. Okay. So now, what is epsilon zz? This is sigma zz minus mu times sigma xx plus sigma yy. Actually, we did not have to use this step, this equilibrium step. I showed it by mistake. It is not necessary to use these two steps. We can directly use epsilon zz equal to 1 by e into sigma zz minus mu times sigma xx plus sigma yy. Okay, so for question number B, I missed something. Okay, I directly put sigma zz equal to minus p here. Okay, but this is not correct. Why? Sigma zz is minus p at the boundary. At the boundary. Okay, so I missed that step here at the start. So I'm sorry for that. So they have given that on the top surface they are applying minus p. So this replacement is possible only at the top part. Otherwise, sigma xx is related like this. Now to show that, at any place on this rubber, we will have this value of sigma xx. We had to follow this step, this equilibrium step. Okay. From there, what did we prove? We proved that sigma zz is constant, and that's why sigma zz was minus p throughout the body. Now, after this step, we can say that sigma zz is same throughout the body. But at that step, it was wrong to directly put minus p by nu here. This was wrong. We cannot do this here. This was wrong. Wrong to put directly here. Wrong. Directly here. Okay. Because this will be true for a problem where the boundary, they have asked that what is sigma xx at the boundary. So there we can directly put, okay, sigma zz as minus p. But for other throughout the body, we will have to find the distribution of sigma zz, and after that we had to replace. We will have to replace in the expression of sigma xx. Okay. So here it was wrong to put it, but in this case, what happened that the sigma zz was constant throughout the rubber body. That's why our answer matched. Otherwise, this would have been a wrong. This would have been a blunder. Okay. So I hope you have learned from this. I forgot to. Anyways, so let's move on to the third part. The third part is the volumetric strain. So I will go to the third part. So anyways, so they told us to find the volumetric strain and the epsilon xx and epsilon yy was 0. So the volumetric strain reduces to epsilon zz. And we know that epsilon zz is 1 by E sigma zz into minus mu times sigma xx plus sigma yy. Okay. So we can, of course, now we can write sigma xx here, sigma. Okay. So let's replace everything. So let's replace sigma zz by minus p. Since sigma xx and sigma yy are equal, so we can replace this by 2 times sigma xx. So 2 times minus p into nu divided by 1 minus nu. Okay. So epsilon zz is what? Let's take this minus sign outside. Minus 1 by E p minus 2 nu square p by 1 minus nu. Okay. So let's see if we have any option with this. So we have option number 2 here. So this is the correct answer for C. So I will again just recapitulate that what we did. So in this case, what they had given that we have a steel. Let us assume that we have a steel casing, and there we are putting some rubber. The top portion of the steel casing was open, and from there they have put one steel on the rubber, and they are applying some constant uniform pressure. Okay. So they have told that steel is rigid, and they told us to find what is epsilon xx, epsilon yy, epsilon zz, sigma yy, sigma xx, and what will be the volumetric strain. So at the boundary, sigma zz was minus p. They are given the traction that minus p is present at the boundary. Okay. From the problem, we can understand that since steel is rigid, so rubber will not be able to move in x and y direction, and that's why its displacement will be 0 in x and y direction. But there will be some displacement in the z direction because it is free there. So we consider that uz equal to uz xyz. Now we also from the question know that the applied pressure is uniform. So our displacement it reduces to only function of z. Now we found out all these epsilons and gammas, and we came to know that our strain matrix has only epsilon zz component. From there, we were able to find that our shear stress components will be 0. Then what we did, so we solved the first part of the problem. Then we had to find what is sigma xx and sigma yy. Now from the problem, we understood that this problem is symmetric, and that's why sigma xx and sigma yy will be 0. And that's why we use the formula of epsilon xx and epsilon yy, and we put epsilon xx tends to 0 because it is given. Suppose if we did not know that sigma xx and sigma yy are equal, we would have used the second formula also. Okay. Here also we would have done say epsilon yy equal to 0, and we would have got something. We would have got two different equations, sigma xx and sigma yy, and the third was with respect to sigma zz, and then we had used the like this equilibrium equation in the z direction, and from here also we would have been able to understand that what will be the value of sigma xx and sigma yy. Okay, so from there you can try it at your home. You assume that okay, sigma xx and sigma yy are not equal. You assume that you don't understand symmetry. You will do what? Epsilon yy equal to 0, and you will have two different equations, and you will be able to find them in terms of z. Okay, sigma zz. Now after that, what we did, we found sigma xx equal to mu times sigma zz by 1 minus nu. Then we used equilibrium equation, and we found out that sigma zz was constant throughout the rubber in the z direction. So we were able to replace sigma zz by minus p in the general equation of sigma xx. Now they told us to find the volumetric strain. So what is volumetric strain? It is the trace of strain tensor. Now from strain tensor, we came to know that only epsilon zz was present. So we used the formula of epsilon zz. We substituted sigma zz and sigma xy, sigma x and sigma y, sigma xx and sigma yy, and we found out the answer. I hope I was able to make you understand. Now, if any one of you has any doubt, you can ask me. Otherwise, I will end this session. If you have any doubt, you can write in the chat. You can unmute yourself. You can speak. It's up to you. Does anyone has any doubt? Okay, since none of you have any doubt, I will be ending this session. I will meet you again in next class on Tuesday from 6 to 8 p.m. If you have any doubt, you can ask that on the forum also. We have a forum on SWAM portal. You can ask there also, and we will be try to reply. Thank you, everyone. Thanks for joining. Have a great day. Good night. Bye. I'm ending the meeting now.